In this lesson, we shall focus on mathematics, closed sets, and closure. Right, having studied open sets, we now pay attention to their complements. A number of results here will be obtainable from their counterparts in the open set section by appealing to what we call De Morgan's laws, namely, for any set X, any collection S sub alpha, alpha and gamma of subsets of X, we have that the complement, which is X minus the union of the S alpha sets, becomes the intersection of the complements. Okay, so now, but also, if you take X minus the intersection, is the same as the union. And this is called De Morgan's laws. We are able to see, therefore, that if you actually take here the intersection of the complement, or you take the complement of the intersection, yes, the complement, which is the minus of the intersection, it becomes the union of the complements. And once again, this is what we call De Morgan's law, or in particular, both of them are what we call De Morgan's laws. But obviously, we can remember the De Morgan's laws, they can be taken like this: A and B, for example, as sets, right? And if we happen to take A and B complement, this will be the same as A complement union B complement. This is De Morgan's law, for example, for the intersection, but also we can have De Morgan's law on the complementation applied to the intersection, to the union. So that the A complement intersection B complement as well. Now, these two properties of what you call De Morgan's laws remain very, very important. And we pay attention to them here, and we continue with our study. Definition 03.1, a subset S of a metric space. Right, so we studied about 12 at 2050. Right, we studied at, say, 2050. So we must go on up to 2150, thereabout. Okay. Now, definition 03.1, a subset of a metric space XD is closed if its complement X minus S is open. This is very important. It gives a characterization of what you call a closed subset S of a metric space, but it's defined in terms of the open set. So in other words, a subset S of a metric space XD is closed. What is a closed set? A subset of a metric space XD is closed, right? If its complement X minus S is open. If that is the case, then we're dealing with a closed set. 03.1 example. In any metric space XD, every closed ball B bar of XR is closed. Okay, this is a very interesting example where we're going to be proving that what we call a closed ball is closed. It doesn't, it looks very obvious that somebody will be like, okay, but it's a closed ball. Really, do we need to prove that it's closed? What are we proving here? We are proving that the closed ball is actually what you call a closed set. And we pay particular attention to the kinds of details that become very important. And let us get cracking with this. Recall that the definition of B bar of X and R, in other words, the closed ball of center X and radius R, contains Y and X, such that the distance between X and Y is actually less or equal to R. And obviously now we actually look at the characterization of the closed ball with the less than or equal to symbol. Now, to prove that B bar of XR is closed, how do we prove that it's closed? In other words, we need to prove it's a closed set. We must show that its complement is open. And this is very interesting. So how do you prove? One way to prove that a set is closed is actually to show that its complement is open. So the complement of the B bar XR is X minus B bar of X and R is open. Right, so and we actually, to prove, therefore, that this set is open, we take a point from it. let Z be an element of the complement of the closed ball. So it is we let Z be an element of X minus B bar of XR, yes. Then the distance between Z and X is actually much bigger than R. Okay, so this is very important. So we are dealing with a set here, and we're saying that we're dealing with the complement of the closed ball. If really this one here, we argue that is the closed ball. Obviously, it has to be a bit round. Let me be more practical here. Right, let him be more practical. Otherwise, somebody will be thinking that it's so weird. Here is a closed ball, say round. B bar of XR is there, and it is our closed set. Now, this is actually living in our zoo of the sets, and it is living in X. And now we are considering, obviously, now the complement of these. So the complement of these will be the region outside the ball. And if this is the case, we actually therefore take Z that is in the complement. So taking Z that is in the complement, it is Z that is in the complement of these. So now, as we have the following, let us take it outside, just making the exterior very tidy. We could shade it, of course. Now we take a point. Z that is in the complement of this region. Here outside this is the region X minus B bar of XR, and we take a point Z in the complement of the B bar. Then we are arguing. Obviously, this is center X and radius R. That is the closed ball definition. We're arguing that if we take the distance between X and Z, this distance is much bigger than R. Of course, it is true, therefore, that this distance here is much bigger than R. Why is the distance much bigger than R? So we're arguing, therefore, that the distance between X and Z indeed is much bigger because the point Z is outside, so the distance is much bigger. It's an exterior point. So what do we then do? We realize that this inequality is true. Thus, put the delta to be the distance between Z and X together with what? Yes, we take the distance between Z and X, and then we subtract R. So we can see that, the distance is too big between Z and X. So we take the distance between Z and X, and then we minus R, the radius. And note that delta itself is positive. So we note, therefore, that delta itself is what? Is strictly positive. Why is delta a positive number? It is a positive number because we're taking the distance between Z and X, which is much bigger than R, and we're subtracting something smaller than the distance. We're subtracting R, and therefore we are taking delta to be this little thing. What is delta? Delta is this little distance here. We're calling it delta. Okay, right. We will show that the distance of the open ball centered at Z of radius delta. So now we're forming a ball that is actually going to be sitting somewhere there of radius of center Z and radius delta. We show that this open ball is actually a subset of the is actually living in the complement. Is living in the complement of the closed ball, right? Which will complete the proof. So let W now be an element of this particular open ball. So we take a W to be inside here. So if we allow W to be living inside the open ball, right, then now we take the distance. We take the distance. So then the distance between W and Z is actually much smaller than delta. It is true, of course, because if you take the distance between W and Z, we argue that this distance is much smaller than delta. Is much smaller than delta. Okay, if this distance is much smaller than delta, it actually tells us that, okay, what do we then know? Now, we can then use the triangular inequality, that the distance between X and W, right, the distance between, this is X, the distance between X and W plus the distance between W and Z is bigger than the distance between X and Z. So we have a triangle. We have a triangle where we've put X there. Can actually just draw a triangle here. So we're going to use the triangle inequality, but in a very, very cunning manner. So we are then saying there is a little point. There is a point X, and then we have a point Z, and then we put a point W, and then we are forming a triangle like this. A triangle like this. But now, if we're forming this triangle, then if the distance between W and X is smaller than delta, of course it is smaller than delta because delta is the radius of this particular open ball. Now, if we take the distance between X and what? And W, plus the distance between W and Z, okay, two sides of the triangle, this will be bigger than the distance between X and Z. Of course, this is the triangle inequality. The sum of two sides of a triangle is greater than the third side. This is it. Hence, now the distance between X and W. Right, so we can manipulate this. So what can we then do? We make the distance between X and W the subject of the equation. Then we move this one to the right-hand side, making it a negative. But the distance between W and Z, what do we know about the distance between W and Z? The distance between W and Z is smaller than delta. So this one is smaller than delta. So that in the end, then we have the distance between X and Z minus delta is actually equal to R. This shows that the distance between W and X, okay, obviously this shows that the distance between W and X is actually much bigger than R. Okay, so if the distance between W is this one here, and X is
Sorry for
much bigger than,
interrupting.
yes, please.
Can you please just explain why? Okay, so I have that DWZ is less than delta, but then now my inequality sign flips, and instead of a less than, I have a greater than. What happened there?
Okay. Yeah, that's interesting. Okay, now let us start to, we're going to do it in two lines. I'm going to just show that one in two lines here to see obviously what they claim that the inequality sort of flips or changes direction. First, let us look at this inequality here. So we are saying the distance between actually X and W, right? And we added the distance between W and Z. We're saying this is greater equal to the distance between X and Z. So if then we want to make a XW the subject, right? So want to make the distance between X and W the subject of the particular inequality. So we agree, therefore, it will be the distance between X and Z. We move this one to the other side, making it minus the distance between W and Z. Right? So in other words, the inequality is correct. But of course, we have more than this because the distance between here W and Z is smaller than what? Is smaller than delta. It's actually much smaller than delta. And so the distance between X and Z, right? So if you look at the distance then between that, so you need to multiply it through by the negative. Because the distance between W and Z less than delta actually means therefore minus this distance would be bigger than minus delta. So in other words, you have minus this. So if you're going to put this, then you're going to put minus delta here. So it is therefore greater than because we multiplied both sides by negative. So this inequality is therefore correct. But indeed, the distance between X and Z minus delta is actually what we have been actually discussing the most. Because if you look at the distance between X and Z, right, X and Z, this one, X is this one, and Z is that one. So we take the distance between X and Z, and we minus delta, which is the radius of this. So we minus this delta here. Then we actually obviously are sure to get R. And this shows, therefore, that the distance, of course, this shows that the distance between X and W is bigger than R. Once we deduce that W itself is not a member of, is not an element of the closed ball, right? So we argue therefore that W is not a member of the closed ball. Why would W not? Because it's not a member of the closed ball. The closed ball contains what? It contains all points X, such that the distance between X and R is, you have center X and radius R. So obviously this pointer would have, if the radius is R, then everything is going to be smaller than R there. But we are saying therefore that the distance is bigger than R, and that puts W outside because the distance is much bigger than the radius. For the radius, for things in the closed ball, the radius must be smaller than R. Consequently, obviously, with W is therefore in the complement of the closed ball. And so every element of the closed ball is an interior point. This is it. Because this, okay, now this is very important. So W is a member of these, right? Is a member of the complement of the closed ball. So every element of the closed ball is an interior point. Thus, X minus BXR is open. Why? Because every element of the closed ball is an interior point. Thus, X BXR is open, and therefore BXR is closed. So, as in the case of the open ball, we are justified to call this one a closed ball. Why is it a closed ball? It is certainly a closed ball because we have seen therefore that it is a closed set. B bar XR is closed. Why is it closed? It is closed because its complement is open. It is closed because its complement is open. So how do we know that this set is open? If obviously this is a closed ball, it's because so every element of the X minus B bar XR is an interior point. It is an interior point. Next question. Right, next point. Unpacking these here. So let's look at example 03.2. Let A and B be real numbers such that A is smaller than B. Let A and B be real numbers such that A is less than B. Then each of the intervals A, B, minus infinity B, from A closed on the A side to infinity is closed. So this is very important. So we let A and B be real numbers with A smaller than B. Then each of the intervals, A to B, including the boundaries, but also minus infinity to B, and also A to infinity. So if you start from minus infinity from the left, and include the point on the right, the extreme point B on the right, or you start from A and then to plus infinity. So we are saying these are closed. These are closed. Indeed, the AB is the same as what? The AB is the same as R. Yeah, okay. So the AB is the same as R. So obviously we're arguing therefore that if you take A, B, and then now we then say you take the whole of R. You take the whole of R. So you subtract the union of this. So if you take the whole of R, if this is R, that is the A and the B, and you minus from it. So you take essentially the complement of the things that start. Okay, for example, if you look at A from A to infinity, negative infinity, from B to infinity. You take the complement of this, so the complement of these will surely be that. Will surely be that. Okay? Yeah. The complement, so, but also, why is this complement so important? Because we are able to see that a set is closed if its complement is open. If its complement is open. So obviously we have already seen therefore that indeed we took the complement of this particular set here. So the complement of this particular set here is closed. The complement itself is closed. But also, if you take the complement of b to infinity, it contains minus b to infinity. So a set is closed if its complement is what? If its complement is open. So we're arguing, therefore, that this set is closed and this one is open. We're taking the complement of this set and we're getting a closed set. A set is closed if its complement is open. So the complement of this set is this, which is open, and therefore this set is closed. This set is complement is this, and obviously, see, if you take from A to B, you take the complement, you go to the left and the right, you see therefore that the complement itself is what is actually closed, and therefore the set here is open. But also this one, this set is closed, and how do we see that? Because the complement is open by dint of the former definition. In a discrete metric space, every subset is
Um,
closed. Yes, please.
so can I
Yes,
please
please.
ask? Okay. So then we've been working with this definition of a closed set, right? So
Yes.
then you're saying a set is closed if its complement is open. If we
Yes.
use like mathematical reasoning, right? Would it be
Yes.
true for me to say that a set is open if and only if its complement is closed?
Well, yeah, that's duality. Yeah, I mean that's
Yes.
very, yeah, that's very interesting. So, but you see, that would be duality. So can you? Yeah, I hear what you're saying. I mean, can we be able to say always? Because now we need to be very careful, obviously. But can we be able to say that a set is open if it only if its complement is closed? Right?
Yeah.
Is that? Yeah. You see, yeah, but you need to be very careful because there has to be quite reference. But you see, I must indicate that open sets. How to define? Because you're saying a set is open if it only if its complement is closed. I mean, that is true for some sets, but is it true always? But we don't use that characterization very often.
Mm.
Yeah, I hear you. It is true for some sets because now the complement of the open set, a set is open if then you take its complement and realize it is closed. Yes, it is true for most sets, but is it true for all sets? Obviously, it's something else. But we don't use that characterization. What characterization do we use for open sets? How do we determine if a set is open? How?
Um, we say that a
Just
set is
easily.
open if every
Yes.
element is an interior point.
Yeah, if every element of that particular set is an interior point, then the set is open. So well done. So that is sort of the characterization we use for open sets and to determine if a set is open. But obviously, I mean, what you are saying is correct. It is true for some sets, but potentially for most sets, almost all sets, or potentially all sets. But obviously, we don't use that characterization very often. We use uh, that of interior points to determine if a set is open, if it contains all its interior points. Okay, good. Thanks for bringing that
Um,
dimension. Yeah.
I'm sorry, I just wanted to ask that so if I was in an exam and you were marking this exam and then you saw that type of reasoning, would you mark it right or wrong?
Well, in an exam, you could be given credit because you're under pressure and your reasoning is correct. Okay. Yeah, I mean, that reasoning will be correct. As much as
Okay.
it's unpopular. The popular narrative is to say a set is closed if its complement is open. We don't normally use the reverse statement of that. But doesn't mean the reverse is necessarily wrong. But as I indicated, it is correct for most sets. So potentially all sets, but it's not a popular narrative. Okay. Right.
Thank you.
Okay, good, thanks. Right. In a discrete metric space, every subset is closed. And this is what we discussed briefly last time, but in a discrete metric space, every subset is closed. And that brought us to the notion that the singleton itself is closed. Why is this so? So obviously we discussed it very briefly last time. And obviously it is a notion that we can always revisit, most importantly, but it actually borders on the fact that the singleton is closed, but not only the singleton, but also those countably finite, countably finite sets themselves are also closed. We actually established that result, and there were justifications for that. And so obviously, I'm sure that in this example, it is just brought in here to reinforce the notion of a set or sets that emerge as closed. Right. So let Xt be a metric space and X0 be any element of X. Okay, so we just have Xt a metric space and we take a point, X0 an element of X. Then X0 is closed. Very nice result. And yeah, it's very interesting because we discussed that, but not even just in a discrete metric space as stated in the example, and also the way we looked at last time. So the question is, then this one is closed. We're proving that a singleton is closed. We're proving that a singleton is closed. Let's look at the proof. I'm sure it's very, very interesting. So we let Z be an element of the complement of the singleton. This means that because Z is an element of the complement of the singleton, it means that Z is not equal to X0. Yes, Z is not equal to X0 because Z is in the complement of X0. Right. And so the distance between Z and X0 is actually a much bigger positive distance. Okay, so in other words, what we're seeing here is here's a set. Here's a point. And now at this point, we take it with x0. Let's just start. Suppose you have x0, and then now we actually, therefore, if that is the point x0, and we are considering the complement of x0, so obviously if you agree, okay, we agree that we have z in the complement. We have z in the complement of this. Okay, suppose x0 lives here, and then we take z in the complement, but also this is more, we can even remove that. So now, for argument's sake, we have a point. And we take z to be an element of the complement of the x0, yeah? Yes, you can write like that. You see, the reason you can write like this is because this is the same as a set that has one element. Okay, so singleton. Right, so sort of the ring. And then now we actually take Z outside that. So it is in the complement. Z is in the complement. And we are arguing, therefore, that this would mean that, if I remove this would therefore mean that Z is different from X, of course, because it is in the complement. And so now if you find the distance between Z and X0, this distance is positive, meaning indeed these points are different. They're not the same point because one is in the complement of the other one, right? Since the distance between X0 and Z is not less than R, the distance between X0 and Z, right, is not less than R, right? So it follows that X0 is not an element of the open ball of center Z and radius R. Let's look at this. We describe here an open ball of center X and of center Z and radius R. And we're arguing, therefore, that because, okay, so this is very important. Very important. We took R to be equal to the distance between Z and X0. So that R is positive. Went on to then say, since the distance between X0 and Z is not less than R, right, it's not less than R. We're saying the distance because they are far away from each other. So this distance is not less than R. It's actually bigger than R, right? It follows that the X0 is an element, is not rather an element of the center of this open ball of center Z and R. So X0 is outside. That's what we're saying. It's outside this open ball because the radius is way too bigger. It's a distance. It's a lot for us to move from here to there. Right. Hence, the open ball of center Z and radius R is a subset of what? It is in the complement of this singleton. Because the distance is so big to move from this center to the center of this, it means therefore the open ball of center Z and radius R, this open ball is in the complement. It's in the complement of the of x0. Yeah, it is actually outside the x0, which means the complement. So the complement of x0 is open. Right, the complement of x0 is open. Yes, that is true, because the complement of x0 contains an open ball. Contains an open ball. It means, therefore, every element of the complement of this is actually can be covered by an open ball. So every element is an interior point of the complement. Also, x minus x0 is open because each of its elements is an interior point, and the theorem therefore is proved. Because obviously, if the x minus x0 itself, if x minus x0, x minus the singleton is open, therefore it means that x0 is closed. Okay, very nice little proof. But we're able to prove, therefore, that every singleton is open. But this is in a general metric space. It's not just in a discrete metric space as discussed in the previous scenario, right? The theorem above tells us that singletons, that is sets consisting of a single point, are closed in any metric space. So we're saying singletons, right, are closed in any metric space. Informally, we say points are closed in a metric space, right? We will see that, in fact, every finite set, this is it, every finite set is closed, as we saw before. And those are finitely countable sets are actually closed. We saw that we can have x1, x2, we can have x1 together with x2. This one will be closed. Why? Because we can write it as a union of singletons. Okay, let's look at the next point. Right, the following result gives properties of closed sets which are akin to those of open sets in theorem 02.5. Let us take a look at this particular result here. So theorem 03.3, you let X be a metric space, then X, and now this is a very powerful theorem, but it's not specific in terms of what metric space we're talking about, but we're then saying X and the empty set are closed sets. So if you let X be a metric space, the whole space is closed, but the empty set is also closed. Right, so if A1, A2, and AM are finitely many closed sets, then this union is closed. So now, if you have finitely many closed sets, then the union of the closed sets is itself what? Is itself closed. If now we take the A alpha, so that alpha is it's an element of gamma, it's a collection of closed sets, then the intersection of the A alpha is closed. The intersection of the A alpha is closed. Okay, let us actually point on this and see what we can do. And see what we can do. Okay, this is very important, but it's worth remembering, and you need to have a nice way of remembering. But it actually reminds us, but now this is very important, that the union must be a finite union. But this, if you have a finite union of closed sets, it is closed, but finite union. But for the intersection, you can go up to infinity. This is a random where alpha is an element of gamma. It's a collection of closed sets, and you can therefore go up to infinity, and therefore the intersection of these infinitely many closed sets becomes closed. But the union, the theorem is weak. It's weak in terms of the unions because it's stating unions as finite, but these intersections can go up to infinity. Okay, let us prove the first result. The first part to say the whole space X is the whole metric space X is actually closed, but also the empty set is closed. How do we prove this? So to prove this, now we realize that in particular X itself, the set X, is the complement of the open set. So in other words, if you take the complement of the X minus the the open set, what you get X. So X itself becomes the complement of the what? Becomes the complement of the open set. And as the empty set is open, right, we have that X itself is closed. Yes, so we've taken the complement of an open set, which is closed, so that uh, the empty set is open. We have that its complement is closed, right? So a set is closed. Obviously, if its complement is open, so X is closed. If its complement, the empty set is indeed open. Next, we can form a set relation, a set equation by saying the whole metric space X minus X. So X minus X therefore produces what you call the an empty set, and therefore the empty set is closed since X itself is what? Since X itself is open. Since X itself is open. Okay, you see, the fact that X itself is open has been established long time ago. It has been established in the sense that the entire metric space, in the entire metric space, every element of the metric space is itself an interior point, making the metric space open, right? So obviously that was established long ago, and I'm sure we'll reinforce that. But in the meantime, I want us to look at B, and B, which is a weak statement, that you're taking actually finitely many closed sets, and we're saying the union property is weak because it's only for a finite union. So B and C are left as an exercise. Applied De Morgan's law to theorem 02.5. Of course, that would be very, very interesting to do. And we can apply the De Morgan's law to theorem 25. But now, this is very important. How do we prove that the whole space X itself is open? We take the complement of the empty set. And if you take the complement of the empty set and we realize that, and as the empty set is open, we have that the complement, we have that X itself is closed. The set is closed if its complement is open. Next. In any metric space, every finite subset is closed. In any metric space, every finite subset is closed. This is the result. So we actually obviously discussing last time. In a metric space, every finite set, because we looked at these sets like containing x1, x2, like we can go up to, yeah, the way this guy. So you can take S1 up to Sm. Okay. So let S be a finite subset of a metric space. Okay, this is the proof. How would you prove that? You'd say let X be a finite subset of a metric space, right? So if X is a finite subset of a metric space, then you can write it like this because it's finite. So we can say S contains S1, S2, S3 up to Sm. Then now we can write it. This is powerful because S is these finitely many elements. It has these finitely many elements. Then you can write it as a union of the of singletons. If which is a finite union of closed sets. So recall that the singletons are closed, right? So because so each of the singletons is closed, and therefore this is a finite union of the closed set. So by theorem 03 point 3b, we have that S is closed. We have that S is closed. We have that S is closed. Okay, because yeah, by theorem 03.2, so the part B is the one that is weak. I said is weak because it is stating right. It is stating the results about the finite unions of the closed sets being closed. So the finite union, if these is finitely many closed sets, therefore the finite union itself is what? Is closed. So that then by theorem 03.3, then we have that this is closed because this finite union itself is closed according to the theorem 03.3 part B. Right. Moreover now, when we were studying open sets, we encountered the concept of the interior of a set. This is it. When we're studying open sets, we encountered the concept of the interior of a set, right? We saw that the interior was defined in terms of points, in that it is a set of all interior points. So we saw that the interior was defined in terms of points, in that it is a set of all interior points, and showed it to be expressible in terms of open sets, in that it is the largest open set of any given set. So this is so powerful. We saw that the interior was defined in terms of points, in that it is the set of all the interior points. Yeah. So the interior is the set of all interior points, and showed it to be expressible. There's a theorem, obviously, in the former section, right? And showed it to be expressible in terms of open sets. So you can write the interior of a set in terms of open sets, in that it is the largest open set of any given set. The largest open set of any given set is called the what? Is called the interior, right? Likewise, in the discussion on closed sets, we will introduce the concept of closure. Likewise, in a discussion of closed sets, we'll introduce the concept of closure in the same way that with the concept of what? Of the interior. Here, in the closed set, an equivalent property is that of the closure of a set, not the interior of a set. This, obviously, we will define in terms of points, and later prove that it is expressible in terms of closed sets. And we proceed as follows. So, yeah, we shall be dealing with the closure, and we dealt with the interior in the former section. Here we shall be dealing with the closure, and dealing with the closure, this we will define in terms of points, and later prove that it is expressible in terms of what? In terms of what we call closed sets. Let's look at definition 03.5. You let X be a metric space and X be a member of the metric space by a neighborhood. What is the neighborhood? This is the definition. By neighborhood, to be abbreviated NBD of X, we mean an open ball containing X, not necessarily centered at X. By a neighborhood, to be abbreviated NBD of X, we mean an open bowl containing X, not, this is very important, it's not necessarily centered at X. So it's not, this neighborhood is not necessarily like an open bowl with a center. Right, so for instance, in R2, you can take the open ball of center, the origin and radius 1. Right, so you can look at R2, Y and X. We can take 0, 0, and then we have the ball, open ball. And then we have the radius, 1. So for instance, in R2, the open ball of center, okay, of center 0, 0, and radius 1 is a neighborhood of the point. Right, yes, that's very interesting. It's the neighborhood of the point because we take X to be minus 1/2, and take this one to be 1/3, and then this point is inside. So we're saying because this point is inside, and this point is characterized by what? Is characterized by minus 1/2 and 1/3. So we're saying that this open ball is a neighborhood of this point. We caution that in certain books, by a neighborhood of a point, right, is meant any open set, not necessarily a ball containing the point. So we caution that in certain books, by neighborhood of a point is meant any open set, not necessarily a ball. It need not be a ball containing the point. So obviously here the neighborhood that is given is a ball, And this lecturer for the course is saying it need not be a ball, it can be like an awkward set. Right? All results stated in terms of neighborhoods are, as defined here, are true, with neighborhood meaning any open set. By neighborhood NBD, we mean any open set containing the point, and vice versa. So any open set containing the point is called the neighborhood of that particular set, and vice versa. With these nomenclature, right, note actually prove that a set is open if and only if it contains a neighborhood of each of its points. Okay, see, this is very interesting because it reminds me of the categorization you gave there in terms of open sets. You say, can we say a set is open if and only if its complement is closed? Okay, so you obviously we had that discussion just a few minutes ago, and we're saying here one characterization that this textbook is giving, this study guide is giving, that a set is open if and only if it contains a neighborhood of each of its points. This is it. So we define we characterize an open set in terms of neighborhoods and interior points. Right. And if and only if it contains a neighborhood of each of its points. So a set is open if only a set is open if you can take each of its points, x1, x2, then there is a neighborhood which need not be, there's a neighborhood for each of these points. Right, there's a neighborhood for each of these points, and therefore we have that this is most certainly the case. Let's move on to the next discussion. I want us to look at definition 03.6. You let XD be a metric space, S be a subset of X. So now, obviously, XD is the overall universal set, the total, the largest possible set. And now S be a subset of X. So we take X to be a subset of X. Right. We continue. Right. Right. Okay. Right, 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 right. Um, right. Okay, yeah, we are still here. We're still here. Okay, yeah, we're saying, okay, let's look at this definition quickly. So if XD is our metric space, or largest possible universal set, and S be a subset of X. Right, so we can do this, yeah? So this is our metric space, XD, and then we form S be a subset of this. S be a subset, yeah? It need not be open, but yeah, S. Right, be a subset of, is inside X. Right, and Z be a member of the X. Okay, Z be a member of the X. Okay, I've not read the whole story, but I'm just putting, if Z is inside, it can be either inside this or there. Right, we say that Z is an adherent point. Right, okay. Right, so we say Z is an adherent point of S if every neighborhood of Z contains a point of S. So if we can form a neighborhood, it's an adherent point. It's not so far like the way I've drawn it, but we say that Z is an adherent point of S if every neighborhood of Z contains a point of S. Just one point. Right. But obviously, we are referring to every neighborhood of Z. So very close to the boundary. So that if you form a neighborhood of Z, then it will contain a point of S. We say Z is an accumulation point of S if every neighborhood of Z contains a point of S different from Z. So now we're for the first time in relation to what you call the adherent point, we have an accumulation point, but for the first time we have that the point of S must be different from Z. So this is very important. Okay, we shall reconcile the two definitions in terms of what the difference is between an adherent point and an accumulation point. The closure of S, denoted by S bar, or what we call a CL of S, is the set of all adherent points of S. The set of all adherent points of S. So yeah, the derived set of S, denoted by S primed, is the set of all accumulation points of S. So this is very, very important. So now, what actually is happening here? So there are points that are very close, very close. So the accumulation points can be a little bit further away, but the adherent points are like, as the word says, are to adhere, to like be sort of in contact, with the boundary. And but now, such that every neighborhood of Z contains a point of S. But for the accumulation points, every neighborhood contains a point of S different from Z. In other words, the point of S, right, may be that the Z itself is a member of the S. Okay, I want us to discuss that very carefully. Just to reiterate that point, because we say that Z is an adherent point, it adheres to S, if every neighborhood of Z contains a point of S. Meaning that obviously in terms of the adherent points, you actually can have that Z itself is a member of S, but we say that Z is an accumulation point of S if every neighborhood of Z contains a point of S different from Z. So obviously now, this neighborhood must contain a point of S that is different from Z. So obviously in this case, it can be the same as that in the case of the adherent point. And here, obviously, it has to be a point different from Z in the case of what we call the accumulation points. So the closure obviously has been defined as a set of all adherent points. So those are that adhere very close to the boundary form what you call an adherent point. And the derived set of S, denoted by S primed, is a set of all the accumulation points of S. So the set of all the accumulation points of S, they actually constitute what you call the derived. The derived set we call S primed. Let's go through quickly this little paragraph here. So let us pause a bit and digest these concepts. For an adherent point P of a set A, we require that every neighborhood of P, this is it, must contain a point of A. Okay, this is very important. For an adherent point, the points that adhere, that attach themselves to sort of the boundary, right? For an adherent point P of a set A, we require that every neighborhood of P must contain a point of A. Must contain a point of A. Such a point may be P itself. However, for P to be an accumulation point of A, every neighborhood of P must contain a point of A different from P. Different from P, but there's no different from P in the case of the former, right? In other words, every neighborhood of P must contain a point of A minus a point of the complement of P, because it must be different from P. All right, it clearly then follows that every accumulation point of a...
Sorry, Sunshine, can you
Yes,
please
please.
just explain that last sentence?
This last sentence, right? Because you're saying, in other words, every neighborhood of P must contain a point of A minus P, so it must contain every neighborhood of P must contain a point of the complement of P. Why must it be the complement? It must be a complement, a point of the complement, because a point of A different from P. If the point is different from P, then it's a point that must be in the complement of P. Otherwise, if it's not the complement of P, then it can be the same as P, which
Okay.
becomes an adherent point. Right, but the accumulation point must make sure that this point is sort of in the complement of the region that contains P. Right. It clearly then follows that every accumulation point of a set, okay, B is an adherent point. Okay, this is very important because these concepts are very close to each other and potentially confusing. But as said here, it clearly then follows that every accumulation point of a set is an adherent point because the accumulation points can be in the complement. Right. And so now we are then saying every accumulation point is actually an adherent point. It's actually an adherent point. Right. In symbols, we can then say the derived, right? The derived set B is a subset of the closure of B. Okay, let's process this one. Obviously, the derived set B is a subset of the closure of the set B. Okay, obviously we're trying to interpret these concepts that are very, very close to each other, right? Is the converse true? Before answering these, let us note that for any subset S of a metric space, if we take Z to be a member of S, an element of S, then every neighborhood of Z contains a point of S. Right? Yes. Because Z is an S, then every neighborhood of the point Z. So in other words, I mean, you're taking S, and then you're taking a point Z inside. Then every neighborhood of Z, then you can get a neighborhood of Z. Every neighborhood of Z contains a point of what? Of S. Right. And now, right, yes. If that is the case, then every neighborhood of Z contains a point of S. Z itself. And so every neighborhood of S, right, is an adherent point of S. So every point of S is an adherent point, um, of S. Okay. That is that S itself, this is very important. Every point of S, we take a point of S, is an adherent point of S. And therefore, obviously, therefore means that every set S is actually contained in its closure. Every set is a subset of the closure of the set S. The example below shows that not every adherent point, this is very important. The example below shows that not every adherent point of a set is an accumulation point. Okay, so in other words, the converse is not necessarily true. Okay, well, in the following sense, we've gone to then say, it follows that every accumulation point of a set B is an adherent point. Every accumulation point is what? Is an adherent point of B. Yet, the example below shows that not every adherent point is an accumulation point. So you can't take the converse of this. Let's look at that example. Right, example 03.4, you consider the set of naturals, right, as a subset of the real numbers with the usual metric. And once again, the usual metric is the one that finds the distance as the modulus or the magnitude. For any m in the naturals and m an adherent point of n, now we can then consider an open ball of center m and radius 1/2. Obviously, in the natural numbers, it's going to contain only m. Of course, yes, because if we take the natural numbers and we say, okay, here is the number line of the naturals. We have 1, we have 2, so you're going to have 1, you have 2, you have 3, and so on. So you can take an open ball of center m. Choose m. M can be any of these numbers, so m is an element of this. So if m is in the naturals, yeah, this one can be m. Ooh, we can have an open ball here like this. Okay, so now we then argue that obviously at this point, this open ball of center m and radius 1/2 will contain what? To contain m. Because now this is sort of discrete, it's broken, it's not continuous. So because of that, then in this open ball is just going to contain only the M. Of course, the radius is 1/2. So the radius is 1/2. We're taking it 1/2 there, so it's not going to contain two. It's going to contain only 1 point. Is a neighborhood of M which contains no element of N different from M. Right, is the neighborhood of what? Of M, but it contains only M and does not contain any element different from M. Thus, M is not an accumulation point of N. Thus, M is not an accumulation what? Thus, M is not an accumulation point of N. Thus, M is not an accumulation point of N. We've actually shown that the derived set of the naturals is empty. Right. In other words, we have shown this by the derived set of S, which you call S primed, is a set of all accumulation points. And we then said it is what? It is certainly empty. So in other words, we actually obviously note a couple of things about this here. And the derived set is a set of the accumulation points. So in other words, we can see that the set of the natural numbers does not even have even one accumulation point. Right. So in the discussion, because its derived set is empty. So in the discussion preceding example 03.4, we saw that for any subset B of a metric space, the derived set B is a subset of the closure of B, and B is a subset of the closure of B. Now, this is very powerful. So if the derived set subset B is it's in the closure, but also B is always in the closure. The closure is bigger because it contains the boundary points. So now we take the union of B primed with B, and therefore it will be contained in the closure. In fact, we have the following very important theorem. Right, so now I want us to quickly go through this theorem and just try to make sense of it. Right, so let's look at the theorem first. Let S be a subset of a metric space. What is S? It's just a subset of a metric space. Then the closure of S is the union of S with its what? With its derived subset. So this is very important. So it gives us, it's an important theorem, that gives us a formula for the closure. To say to get the closure, just take the closure of S, just take S and take the union with what? With the derived subset of S, right? With the derived uh, set of S, and the derived set of S with the union of S will give us the closure of S. We have already observed that S union S primed is actually a subset of the closure. This is what we have seen before. Right, so we have obviously been able to see that part over there. In particular, we saw it here. Yes. Right. We're able to see that we've already observed that B primed union B. We're going to go a little bit into detail, obviously, of this at some point and just try to understand the geometry here of the sets. Right. We've observed that B union B prime, so S union S prime is in the closure, right? So it remains to show that the reverse containment, right? So now we're going to start from the closure and show the reverse. So let us show that the closure of S is in the S union S prime. So let X be an element of the S bar. If X is not in S, X is not in S, then given neighborhood N of X, we have that this neighborhood contains a point P of what? Of S. Since X is an adherent point of S, because X is not in S, then it would follow that it is an adherent point of S. As X is not in S, X is not in S, it follows that P is not equal to X. Yes, P and X are different. Right. Thus, N contains a point of S different from X. So obviously, thus N contains a pointer of S different from X, which is the point P, which is different from X. Since N is an arbitrary neighborhood of X, we chose N to be a neighborhood of X, but arbitrary, a random one, right? We conclude that every neighborhood of X contains a point in the complement of X, right? This proves that X is an accumulation point, right, of S. Yes, it proves that it is most certainly an accumulation point because P and X are different, and therefore I prove that X is an accumulation point. If they were the same, it would obviously border on what we call the former, right, the adherent point. Right, so, but here it is an accumulation point because it need not in the case of the accumulation point, then it must be different, necessarily different from the point must be different from the other from Z, say. So this proves that X is what? X is an accumulation point of S because of the difference in the X and the P. That is, X is an element of S primed. All we all in all, we have shown that the closure of S is a subset of the S union S primed, the derived set. Therefore, we have shown both directions of the set inclusion. Right, yeah, this is very important. But now, you take note of it, but also it is a very important categorization. One thing that you can never forget here is the statement of the theorem that says that let S be a subset of a metric space. Then how can you find the closure? You can just take the set S and take the union with the derived set S, or the derived set of S. In the end, if you have the derived set of S with the union of S, then you have the closure. It's one way of calculating the closure of a set. Right, I'm sure that we've discussed a little bit these things, and it was pretty interesting to discuss this and just to look at the following quickly and try to make sense of this. In other words, the foregoing result says A, B. Let's look at A. The closure of a set S consists of S together with all its accumulation points. That's what we're saying. So we're saying, in particular, to get the closure of a set, you can just say, take the set S together with all its accumulation points, and then you get the closure. I mean, the question is, what is the quickest way to find the closure of a set? Okay, somebody will say, okay, according to that theorem, you take this set S and all its accumulation points, and then you have the closure. Next. Now, and in part B, P is an element of the closure of S if and only if okay, it's very important, if and only if every neighborhood of P has a non-empty intersection with S. Okay, so in part B, in other words, the foregoing result says that if you get an element of the closure of S, P is an element of the closure. What is the necessary and sufficient condition? If and only if every neighborhood of P has non-empty intersection with S. Okay, that's very interesting. It is important to note that an accumulation point of a set A need not be an element of A. Okay, we have already been stating this one. It necessarily is supposed to be different. But yeah, it can be different. So it need not be an element of A. It is an easy, as an easy example, note that every neighborhood of 1 contains an element of the interval 0, 1. Every neighborhood of 1 contains an element of the interval 0, 1. Because if you look at the interval 0, 1, right, 0, 1, yeah, as an easy example, note that every neighborhood of 1, right, a neighborhood of 1 contains an element of the interval. Yes, every neighborhood of 1 will contain an element of this interval. It's just some element of this interval there. Thus, 1 is an accumulation point of 0, 1. 1 is an accumulation point of 0, 1, which does not belong to 0, 1. 1 does not belong to 0, 1. Yet it is an accumulation point of 0, 1. Yet it does not belong to the interval because it's of the open circle. On the other hand, every point of 0, 1 is an accumulation point of 0, 1. On the other hand, every point of 0, 1 between 0 and 1 is an accumulation point of 0, 1. I said already, Obviously, we have already seen an example of 1 being accumulation of point of 0, 1, yet it does not even belong to 0, 1. So the accumulation point did not belong to the set. This is what we are saying here. Right, I'm sure it was awesome having this discussion here. It's just 10. Right, obviously we started it about 2050 until we had to run to 2150. And we have added extra 10 minutes, taking us to get to 22. Okay, this recording which I'll send you, I know very well with the other recording which I'll also receive. And then you can try to process this and we can always look at what. But yeah, we'll try to make sense of the closed sets and properties of closed sets and some results we need to know about closed sets. Yeah, very interesting results. In particular, I mean, the height of our discussion today has been every finite set is closed. Every singleton is closed. Right, and also, most importantly, the closure of a set is actually equal to the union of the set with the derived set of that set. The closure of S is the union of S, union S, the derived set of S, but also the derived, right, what you call the derived set of S. So the derived set of the naturals is empty. Meaning that obviously the derived set we have already said already, right? The derived set is the set of all accumulation points. So now the natural numbers has no accumulation points. It doesn't have any accumulation points, right? Because the derived set of the natural numbers is empty. Just a realization there. All right. I must thank you for joining us. It was awesome having this discussion. We shall meet again. Shall send you a recording tonight.
Okay, no problem. Thank you, Sunshine. I'd like to schedule another meeting for tomorrow. Are you available?
Yes, yeah. We can have our lesson tomorrow.
What time are
Yeah.
you available tomorrow?
Okay, you can play anything outside, yeah, outside 2 and 4, between 2 and 4, outside that interval between 2 and 4, outside that. Because I've
Outside of
changed
the
up.
interval of two and
Yes,
four.
yes, yeah, outside between like 4 and 6. Excuse you, between 4 and 6 in the evening.
Okay,
Yeah.
no problem.
Okay. Thanks, Sandy. All the
Um,
best. We'll talk then. Yeah, we'll keep you posted today of the recording. Okay.
okay, thank you very much.
Okay.
Bye,
Thanks.
Sunshine.
All the best, everybody. Have a good evening. Thank you.
You
Goodbye.
too.
Thank you. Goodbye.